Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In the last lecture, we discussed about the hydrogen atoms energy levels and emission spectrum of hydrogen atom, and we also discussed that the energy levels of hydrogen atom were n square fold degenerate. Today, we will discuss about the hydrogen atom's eigen functions. To remind you, the eigen functions of hydrogen atom that we had, we expressed them in terms of this psi as a function of r, theta and phi, and the indices that it depended on are n, l and m, where the total wave function is given by two different functions, one radial function which depended on n and l, and the angular function which depended on l and m. The angular functions are the simple spherical harmonics that we have discussed in case of angular momentum operators eigenvalues, and the radial functions that we derived in the course of our discussion are given over here, where it has 1 over r rho to the power l plus 1, where rho is the dimensionless coordinate given by z over a n, where a is Bohr's radius and n is the quantum number that goes from 1, 2, 3, so on and so forth. R is your internal coordinate. So, and again L is the angular momentum of the electron. This quantity and this quantity we obtained by from the asymptotic solution of the radial wave function, and then we have this main body of the solution where the main body of the solution is expressed as a power series expansion, where j goes from 0 to j max, and j max is given as n minus l minus 1. So, here to remind you, n goes from n as 1, 2, 3, so on and so forth. For a given value of n, the L value goes as from 0, 1, 2 until n minus 1. And for a given value of L, m goes from minus L to plus L in the step of 1. So, therefore, for a given value of n, I have n number of L values, and for a given value of L, I have 2L plus 1 number of m values. Together, I see that for an energy with energy level of E n, which was given as minus 13.6 z square by n square, the energy level depended only on n quantum number, whereas for an energy level of E n, I have n square number of eigen functions possible for this. Now, we would discuss what are these eigen functions and how we can write them. So, here I have expressed only the radial part. We would for the time being will not consider the angular part of the solution, because we already know the properties of the angular part of the solution. The angular parts are given by the spherical harmonics, which we have obtained in their normalized forms. So, we can simply discuss now the radial part, and at a later point of time we will combine the radial and angular solution to obtain the full solution. But before we do that, let us understand a few more things about the radial part of the solution. So, this is the general form of the radial part of the solution, where b is a are the coefficients which are given by this expression that we have derived. Now, for n equals 1, we have the possible values of L is it goes from 0 to n minus 1, and n minus 1 is 0. So, only one value of L is possible, that is L equals 0, and given that L is 0, there is only one possible value of m, that is also 0. So, now we have this wave function psi 1 0 0 r theta phi, where this is first is n L m, which is r n L depends on r, and y 0 0 depends on theta phi. we know this y 0 0, this was simply 1 by 4 pi under square root, which was a constant, and we would now look at what is this R 10. So, now we have for n equals 1, the energy is simply minus 13.6 electron volt for hydrogen atom, and I have got only one solution, one eigenfunction corresponding to that, and I call that psi 100. For n equals 2, I have two values of L, that is L goes from 0 to n minus 1, which is 0 and 1. These are the two values. But for L equals 0, again I have 12 plus 1 number of m values, that is, since L is 0, 12 plus 1 is 1, and that I have only one value of m, and that is m equals 0, and the function that I have is psi 200 as a function of r, theta and phi. This again I can write down as r 20 r y 00 theta phi. You see, both in 100 and 200 I have the same angular function operating, and its energy is minus 3.4 electron volt for hydrogen atom. Now, when L equals 1, I have 12 plus 1 number of m values. So, therefore, m goes from as 0 or plus minus 1. So, there are three labels here. How would I write them? I would write them as psi 21 1, psi 21 0, psi 21 minus 1. Say this is n, same for all three, L again same for all three. All the three functions, they differ by their m values. How would I write this? I will write this r 21 r y 11, r 21 y 10, r 21 y 1 minus 1 theta phi. So, you see these three quantities, these three eigenfunctions have same radial part, because the radial part depends only on n and L, but they have three different angular functions y11, y10, y1 minus 1, and we have already seen in our previous discussion on the angular momentum eigenfunctions what are the functional forms of y11, 10, 1 minus 1. Just to remind you, they would have explicit dependence on theta and phi coordinates. Now, what are the energies corresponding to this? Energies of these levels will depend only on n, and we see that this and this, all these three functions as well as psi 200, all these four functions have same n value. So, therefore, their energies are same minus 3.4 electron volt. So, there are four levels of four functions of same energy here, and here E n equals minus 13.6, I had only one function. So, now I see that for n equals 2, I have four functions. So, therefore, this energy level is fourfold degenerate. When I look at n equals 3, you can very well do the same exercise. You would find that I have 9 levels of degeneracy, that E 3 will be 9-fold degenerate. Now, there is a shorthand notation for these wave functions. Instead of writing this psi 211, psi 210, psi 2 minus 1, we have a shorter way of writing this wave function. This is what we know as atomic orbitals. For example, when n equals 1, we call that 1, and then we look at L value. So, we call this n as the principal quantum number. L is the azimuthal quantum number, because it corresponds to the azimuth, the angular momentum coordinate, and m is your magnetic quantum number. And why we call this magnetic m as magnetic quantum number, we will discuss in a few classes. So, n equals 1, L equals 0, M equals 0, we simply give it as 1s, s represents L equals 0. L equals 1 is given as P. So, this label we have 2s, and this label when n is 2, L is 1, we have 2p. And for L equals 1, I have 3 possible values of M. So, 2p plus 1, 2p minus 1, 2p 0, 2p 0. So, these are written down in complex form, but we would also see that we can convert them to real form, and in that case we will call them 2px, 2py, 2pz. So, they represent some linear combination of these functions would actually give you 2px, 2py, 2pz that you know. So, we have 2s and 2p, x, 2py, 2pz, these are the 4 functions. Similarly, for 3 we have 3s, 3p, 3p will have 3 labels, and 3d where L, because for n equals 3, L can be 0 or 1 or 2. So, this will be called 3s, this will be called 3p, and this will be called 3d. 3d label will have 5-fold degeneracy, because they will have M as plus minus 2, plus minus 1, plus and 0, and for 3p M values will be plus minus 1 and 0, and for 3s M value is 0. So, if you count them together we will have 9 different functions, and they are 3s, 3p, 3d and so on. But you see, for hydrogen atom the energy levels 3s, 3p, 3d they have same energy, 2s, 2p they have same energy, 1s has a different energy compared to 2s and 3s. And you will see that when I go to n equals 4, n equals 5 and so on and so forth, the energy levels will be the degree of degeneracy of these energy levels will keep on increasing, but I can only distinguish energy levels according to n quantum number or principal quantum number. So, for hydrogen atom or hydrogen like atom, that means when I have helium plus or lithium plus 2 plus and so on. So, the lowest energy level is 1-fold degenerate, the second energy level is 2-fold degenerate, because this corresponds to 2s, 2p, this is 1s, the third one will be 3s, 3p, 3d, 9-fold degenerate. But this way of writing energy level is true only for hydrogen atom or hydrogen like atom when there is only one electron. Only when there is one electron you have this kind of degeneracy. When you have not hydrogen like atom, for example helium without a plus charge, or lithium or any other heavier elements where you have more than one electron, this beautiful degeneracy that we see in hydrogen atom is no longer there. And from your atomic structure knowledge that you already are aware, that you would see that 1s will have the lowest energy, then 2s and 2p, while they were degenerate in case of hydrogen atom, they will no longer be degenerate for heavier atoms. So, this will be 2s, this will be 2p. So, that the 2s will be again 1-fold degenerate, 2p will be 3-fold degenerate. So, these 4 levels will split into 2, one will have 1 level, another will have 3 levels, and similarly you will have 3s, 3p, 3d, they will also split in energy. This is true for all systems which have more than one electron, where the energy levels can be given as n, can be identified as n plus L rather than only n. Only for one electronic system we have this kind of degeneracy, but for other system where we have more than one electron, the degeneracy pattern is changing. For example, if I ask what is the degree of degeneracy of the second level of hydrogen atom and the second level of helium atom. Second level of hydrogen atom will be this one, because this is the first energy level, this is the second energy level. The degeneracy of this level is 3 plus 1, 4. But when I look here helium atom, the second energy level is this one. and this one is a non-degenerate, or the degree of degeneracy is 1. So, we have to keep this in mind, that this kind of degeneracy is applicable only for one electronic system. All right. Now, we have come to a point where we would see that we would want to write down the functional forms of these radial functions. To do that, we will first take n value of 1, and since n value is 1, I have only one value of L possible, and that is 0. So, I am writing down I will try to write down the functional form of this radial function of 1 over R10, and then I look at the right hand side. I have 1 over R, rho to the power L plus 1. What is L? L is 0. So, therefore, this will be simply rho, but what is rho? Rho is Z over A n R, but I already know that n is 1. So, therefore, I need not write this n over here, because n is 1. So, therefore, rho becomes Z over A r, rho to the power L plus 1, L is 0. So, this is simply this quantity, e to the power minus rho and then I have sum. How many terms would I have in this summation? J goes from 0 to n minus L minus 1. N is 1, L is 0, and therefore, n minus L minus 1 is 0. So, J goes from 0 to 0, that means only one term, and I will have a single term, and that is B 0. If I simplify this R and R, they cancel out. So, I have B 0, which is the coefficient over here, I do not know its value, Z over A e to the power minus Z over A r. So, this is the radial solution of hydrogen atoms 1s orbital. What functional form does it have? It has some constant, we still do not know what is. Z over A, Z is the nuclear charge, which is 1, A is the Bohr's radius, which is 0.529 angstrom. So, this is again a constant. So, together these are constants, and what I have is simply an exponentially decaying function, where the exponent is minus Z over A r. Now, we see that we have one unknown in this function, that is B 0. We need to find out that value of B 0. How would I do that? When I have a function that is going to define the state of the system, I know that this function should be normalizable. So, now I will try to normalize this function, and then by normalizing this, anyway I would be able to find one constant, and that B 0 value will come out from there. So, I would now show the normalization procedure here. Please pay attention, there is an important point that you must remember when you normalize this radial function. So, my task at hand is to normalize this function. So, therefore, I wrote the square of this function psi star psi. What is the coordinate? The coordinate is r, which is the distance between the nucleus and the electron, which goes from 0 to infinite, and then I have to integrate. So, the volume integral that I will have is r square dr. Often students make mistake by writing here only dr, and that would be wrong. Just to remind you, we had the volume integral d tau in Cartesian coordinate, we wrote dx, dy, dz, that was all right in the Cartesian coordinate, but when we came to spherical system, spherical coordinates, this dx, dy, dz converted into r square dr sin theta d theta and d phi. So, when I am integrating a radial function, my volume integral is not dr alone, rather it is r square dr. When I am integrating a theta function in the theta, the azimuthal angle. So, in this case the volume integral is not d theta, this is sin theta d theta. This we used when we are normalizing the eigen functions of angular momentum operator. When I normalize a phi dependent function, I have only d phi. So, this is very important to remember. Since we are only discussing the radial part of the solution, our angular part is separately normalized. So, therefore, I am going to normalize only along this radial coordinate. So, I have this r square dr as the volume integral. So, now I would see 0 to infinite r square and then the square of this function, which is where I see b 0 is a constant, and so b 0 square z over a square, these two constants I take them out, and the square of this function is simply minus. Now, we have to solve this integral. To do that, we will take help of a relation where you can see when I have a function x to the power n e to the power minus q of x, the result of that is simply factorial n divided by q raised to the power raised to n plus 1, where q has to be positive. That means, this exponent function must be negative, which is the case here, and n must be an integer greater than minus 1. So, here n is 2, because I see here x to the power n e to the power minus q x. So, here n is 2 and q is simply 2 z divided by a. So, the result of this, let me first write down the constants that we have. Result of this integral is 2 factorial, which is 2 n factorial divided by q, which is 2 z divided by a raised to n plus 1. Since n is 2, I have this to the power 3. Now, when I simplify this, I see b 0 square, I have here z over a square and here z over a cube. That gives me z over a here, and you see 2 to the power 3 and 2, they give me 1 by 4, and this quantity, if this function has to be normalized, this quantity should be 1. And how is that going to be? That is going to be if my b 0 is simply this quantity. Now, I obtain the value of v 0 by normalizing this function. So, what would be the normalized function r 1 0? This function will simply be 2. I have z over a to the power half, here z over a. So, the function is 3 by 2 and an exponentially decaying function. So, you see here I have a constant, because z is nuclear charge, a is Bohr's radius, so and 2 is a constant. So, this is a constant multiplied by an exponentially decaying function. So, if I plot this function, r goes from 0 to infinite, you will see this will be simply an exponentially decaying function. For large value of r, this function will become 0. And this is this would be within this limit, this would be a well behaved function. So, I now have an idea about how r 1 0 looks like. So, now what we would do is that we would discuss the next function, that is when I take r n as 2 and I consider L is 0. So, that is 2 0. So, here again, so n is 2, L is 0, 1 over r, rho is z over a n. So, z over 2 a, n is 2 here. So, that is why I am writing 2. This is raised to the power L plus 1, L is 0. So, raised to the power L plus 1, that means simply this quantity z over 2 a into r, e to the power minus rho, which is simply z over 2 a r, and j equals 0, this summation, the power series will have going from j equals 0 to n minus L minus 1, n is 2, L is 0. So, therefore, this will have j equals 0 term and j equals 1 term. So, j equals 0 means b 0, j equals 1 means b 1 rho, rho is of course z a by n. So, now I see here r and r will cancel out. So, I have z over 2 a e to the power minus z by 2 a r, and then I have this B0 plus B1 rho. How do I get this B0 and B1? Remember, when we had 1s problem, we had only one unknown B0. If I had only one unknown, I could have normalized this function and obtained that. But here I have two unknowns, B0 and B1. So, therefore, I cannot only normalize the function and obtain the full solution. Rather, I have to find one more way. What would be that way? I know that B0 and B1 are related to each other through this recursion relation. So, now we will obtain what is B1 in terms of B0. So, I see I wrote down at the left hand side B1, that means I am considering j equals 0. So, B1 will be some function some constant multiplied by B0, where the value of this constant is given by this relation. Let us find this out. So, 2 j, since j I am talking about B0 to B1, so therefore, j is 0, L I am talking about 0 function, so L is 0 plus 1 minus 2 n, what is n? N is 2, so therefore, this is minus 4 divided by j plus 1, that is 1, j is 0. So, multiplied by 2L which is 0, j which is 0, 2. So, you see we have 2 minus 4, so that is minus 2 divided by 2. So, you would see this is minus B0. So, we have B1 related to B0. How is it? That B1 is simply minus B0. So, therefore, I write here B0, and in place of B1 I write minus B0 rho, and now I can remove this B0 out of this, and I have z over 2a 1 minus rho, and I can put this rho as z over 2a r e to the power minus z over 2a r. Now, I see, of course, B0 value is not known. I can normalize this function to obtain B0, and to normalize this function I would simply be using this relation over here to do the normalization, and suppose I have my B0 which will be a constant and this is a constant. Now, I look at this functional form of this 2s function. What do I see? I see an exponentially decaying function and a polynomial. This polynomial, so if I draw now the function as from r goes to 0 to a very large value, I would see that this would have been an exponentially decaying function, but it is multiplied by a polynomial where this value can have a value, this term can become 0. When would this become 0? This will become 0 when z over 2a into r is 1, or r is 2a over z, and for hydrogen atom when z is 1, this is over 2a. So, at this value 2a over z, this function has to become 0, and for larger value of when r is greater than 2a by z, this term will become greater than 1. So, this function will become negative. So, for r equals 0, I will have this term becoming 0. So, I will have exponentially decaying function. So, this will keep on decaying until 2a plus z, and then this function will become 0, and then it will become negative because the second term is greater than the first term, and but it would be becoming negative, but then I see for larger value of r, the exponential function will take over, will dominate, and then this will pull it up and the function will become 0. So, now I see that the R20 function will have at a particular value of r will develop a node. So, this is a radial node. Remember, we did not experience that radial node in case of 1s function, but for 2s function we experience this radial node at the value of 2a over z, but at large value of r, this function tends to 0. We will continue our discussion with the other eigenfunctions of hydrogen atom in our next class. Thank you for your attention.